Welcome to Machine Learning Analog Implementations by Nicholas Sika. So in this slideshow, we're going to start with the advantages and disadvantages of machine learning models with analog hardware. Then we're going to go into some different models like the support vector machine, the Boltzmann machine, and the brain-machine interface. So what are the advantages of using analog? There's more precision to certain functions that you just naturally cannot get on the digital side. There's less area and quote unquote simpler circuits. There's lower power dissipation, lower voltage requirements, and allows for a wider range of activation functions to use with the machine learning models. There's quotes around the simpler because while the implementation or the idea behind it is simpler, uh, a lot of analog design is not really simple. And most of these are also kind of on a case by case basis. Like in one case, this may be so, but in another, like the digital side may be better or simpler. The analog disadvantages is if there's only a certain part of the circuit that's analog, you need to have some overhead converting from analog to digital. While the multipliers are simple, the add and subtract units really are not. You need to finely control voltage on capacitors, which is not ideal. It's very difficult to do. Leakage can cause stored weights to decay over time. And there's a thing called weight saturation, which causes networks to not be able to increase their weight magnitude easily. And while it can be worked around, it's a issue when it comes to analog machine learning designs. It's kind of like the weights are just so like stuck in what they are that you can't change them. And there's a constant battle against noise in analog circuits. Now we'll go into the support vector machine uh, model. The support vector machine is a classification technique, and it provides powerful tools for learning models. It's not really a model in itself. Um, and it's held back by constrained quadratic programming problems, which can be easily sped up at the circuit level. And this is one of the best problems for analog circuits to tackle machine learning. It's one of the areas that has the most papers about implementing an analog design. And at the bottom is a figure showing kind of the support vector machine block diagram. The big bottleneck for SVMs in general is integration. As you can see, the equation is not a simple one. And if you do it in the digital domain, you have to discretize the differential equation, and then you have to do a modified Euler's method on it. And that's not really the ideal way to go about it, because why would we do that when we could just keep it as a continuous function, which is where we go to analog support vector machines. It's easier to do the continuous time calculations just because how analog is, it's continuous. You don't need the overhead of discretizing or like the complexity of discretizing, and it's more precise. And there's a diagram of like the traditional and then the neural network model. SVM learning and classification, you don't need any analog to digital converters. You use the intrinsic properties of transistors, so you're kind of exploiting how transistors naturally work. You don't have to do anything extra. There's no dedicated resistors or op amps needed for this design, and it can be the best case of use for it is a highly efficient smart sensor. And below you can see some plots of Gaussian peaks and stuff like that. One of the big uses for SVMs, or one of the big uses in this paper, was a Gaussian kernel. And there is overhead with digital to analog converters with this Gaussian kernel. There's on-chip learning capabilities, and they were talking about how there's scalability issues in the end with this Gaussian kernel. The large sample data requires a lot of die area, and they kind of manage these scalability issues using a gradient descent type algorithm, which is a naive algorithm. It doesn't cover all cases. And below you can see the block diagram of the Gaussian kernel and their results from the analog design. Well, half analog, half digital design. And you can see that there's a huge decrease in supply voltage, among other things. Next up, we'll go into the Boltzmann machine. Boltzmann machines come in kind of different flavors. There's the original Boltzmann machine, which is a stochastic model, and then there's the chaotic Boltzmann machine, which is a deterministic system. The deterministic systems in general are based on pseudo-Billiard dynamics of coupled nonlinear oscillators, and they use continuous valued neuron activations to represent expected values. So you kind of have this pool that they try to model after like brain synapses, and they use weights to decide how it'll go around the pool. One of the uses of a Boltzmann machine is as a reservoir. It's good for its high computing ability, and you can actually see the reservoir on the previous slide. It's good for its high computing ability. It's attractive for time series prediction, kind of like predicting what will happen at X time. And it can achieve complex motion, and there are no digital to analog or analog to digital conversions needed, which is great because we won't have any overhead. And one of the biggest papers on CBM was based on analog oscillator circuits. This requires no random number generation, which is a huge topic, and it would be difficult to implement. But it requires a weight storage mechanism if you were to use more than 3 neurons. There's predicted lower power consumption with non-volatile analog memory. They didn't actually try using non-volatile analog memory, or they don't have non-volatile analog memory. It's just like a prediction on where it could go in the future. There's a trade-off with this between precision and operating frequency, and it has a lot of room to be improved upon with future papers. It's a pretty good starting point for a lot of papers to jump off on, and it has a lot of room to grow and be able to pump out more papers like it. And the last topic is the brain-machine interface. So this one's actually, in my opinion, the coolest. It'll allow people that got limbs taken off or from accidents to be able to control it with their mind, which is crazy. The neural network helps kind of identify what certain signals from the brain mean. This historically was usually done on a computer that's like in a pack or separate from your brain, and it consumes a lot of power. And the integrated circuit makes it compact and lower power, and I could actually go into your brain. I don't know if anyone would want that, but the RF components obviously need to be analog, but it can be implemented with analog floating gates. As you can see, their design allowed for lower power dissipation, a more complex design, and lower supply voltage, which are three huge improvements when it comes to this design. The classification rate was lowered from this design though, which could be bad, but there's room for improvement definitely. So in conclusion, analog design isn't perfect. Designs can be better with analog, but you can't kind of force the analog designs into a digital design because it's kind of a trade-off game, and if you try to like the conversion overhead alone could be very problematic. Like I said, there's always trade-offs with analog. You have to battle noise. Sometimes designs aren't better, and sometimes designs get needlessly complicated from analog. And it's a very promising area with a lot of innovation, and it allows for better designs, more complex designs, lower power consumption, a lot of very big positives for integrated circuit design, and a lot of very big positives for machine learning in general. So thank you for watching.